All right, now that we have a definition for matrix multiplication, we can express a system of equations in a new way. From time to time, it becomes useful to express a system as a product of matrices, as the following example. So let's take a look at how we can do this. And again, this isn't super complicated and should make pretty good sense. So let's take our example here. And this will just be a system of linear equations. Plus 5x cubed equals 2. And our third equation, x1 plus x2 plus 2x3 equals 7. And what we want to do now is express this using matrix multiplication, or represent this system using matrix multiplication. So we start out first by taking A to be equal to the 3 by 3 matrix that represents the coefficients on the system. So 3, 2, minus 1, 1, 0, 5, and 1, 1, 2. So that's our matrix A. So just taking the coefficients off the variables. I'll have another matrix X, which is going to be a column matrix, X1, X2, X3, that represents the three variables, three unknowns. And we'll also have a matrix B that is going to be equal to a column matrix 4, 2, 7. And that's representing the numbers on the right-hand side of our system over here, 4, 2, 7. Again, this is just dissecting the matrix multiplication. If we sort of think about unmultiplication here, if you will, of these matrices, then we can represent our system of equations in the following way. Ax equals b. And I'm going to go ahead and call these vectors because x and b, in fact, are vectors. So I'm going to use its vector notation. So this is now a representation for the system of equations that we've got above here. And again, what we've done is essentially unmultiplied the variables from the left-hand side of this. If you think about what this looks like, then we can rewrite this as just kind of throwing in all the numbers here, 3, 2, negative 1, 1, 0, 5, and 1, 1, 2, times the variable matrix, x1, x2, x3, and that's going to be equal to the column matrix 4, 2, 7. Then if we were to actually do the multiplication here, if you took first row times this column, you get 3 times x1 plus 2 times x2 minus x3, which is exactly what we have on the left-hand side of the equation in the system. So really, we've just unmultiplied. Now that we know how to do multiplication, we've sort of reversed that multiplication process to take this system and represent it this way. This can have some advantages for certain types of solving problems. It turns out that working in this form, this AX equals B form is pretty convenient. Obviously, we still have our augmented matrices. We could represent our system of equations here with an augmented matrix as well and solve it that way. But this gives us an additional way to solve. And again, in certain circumstances, using this AX equals B form will be the form that we need to use to get the solution we're after. Other thing we can do is talk about vector forms. And this is a really useful topic here and pretty important. So let's talk about that. And here we're going to go ahead and let x be an n-dimensional vector. And the vector can be written out as a column matrix in the following way. We've already seen this in that previous example. So we can represent any vector now as this kind of a column matrix. And we define the set of all n-dimensional vectors with real components as the Euclidean n space, and we use that as R of n. So R sub n now becomes the space for which all of these vectors live in. So if we have a three-dimensional vector, maybe we've got x being equal to 1, 0, 5, then this vector lives as part of R3. This is the three-dimensional space for which that vector would exist in. So now that you have that kind of a representation for vectors and for the space that we live in, we can use this to form a new representation for solutions to systems of equations. So let's see how we do that. Here's an example. I think in a lot of cases, just seeing how it's written out is the best way to view these. So 1, 0, 0 going down, and 0, 1, 0, minus 1, 2, 0, and 0, 0, 1. And we've got minus 1, 1, 1. Okay. So here's our augmented matrix. And we can represent this then, just rewriting this in its normal form. I would have x1 minus x3 equals -1 from the first row. The second row would say that x2 plus 2x3 is equal to 1, and x4 equals 1 from the third row. Now we would also notice that I have no leading 1 in the x3 column, so that means that x3 is a free variable, you'll remember, or independent variable. So x3 equals x3. And this was fine. And generally, we would take the next step on this and go ahead and write all of these in terms of the free variable. So then we would have that x1 is equal to -1 plus x3. x2 is equal to 1 minus 2x3. x3, of course, is free. That's equal to itself. And x4 is fixed at 1. So this is generally where we would have left off. But now that we have this vector form or vector representation for how we do this, and we've got some scalar multiplication, we understand what that is now, we can rewrite this one more time, and I can make the left-hand side over here into a column matrix. So this is going to be x1, x2, x3, and x4 as a column matrix. And if I extract out the constants over here on the right-hand side, noting that there's no constant added to x3, we can make that a 0, then I can turn that into a column vector, or a column matrix rather, as -1, 1, 0, 1. Again, the 0 coming from the fact that there's no constant added to x3. And then we would add to that x3 times, and now I'm going to pull off the coefficients from everything in front of x3. So 1, 2, 1, and this is a constant that ended up right here in that constant column matrix. So it would have a 0 there for the x4 piece. So we get 1 minus 2, 1, 0. So this now becomes the vector form for that solution. This means that all the solutions in the system can be written as the sum of the first vector and multiples of the second vector. So it gives us a different way to think about solutions now by looking at multiples of this second vector plus the first vector. And every solution to the system has to follow that rule. So this again gives us just a different way to think about solutions now in this vector form. So why don't you try below to see if you can represent the system that's given in a vector form and see how that goes.